All right, this video is going to talk about a couple of special patterns within factoring. And in order to understand those patterns, let's take a look at sort of where they come from. Now, you might notice this red trinomial over here at the right that we want to factor. And it might stick out to you that there are perfect squares, 16 and 9, in the front end and in the back end of this trinomial. Now, perfect squares are something in math that we can sort of take advantage of. And again, the reason that I kind of point those out is take a look at the couple of patterns over here at the left. We've got a 3x minus 4 and a 3x plus 4. And if I go ahead and FOIL this together, right, the first and the last and the outside and the inside, well, the first is going to be 3x times 3x, or 9x squared, because we were multiplying the same number times itself. Again, we're going to get that 9, that perfect square. Then on the outside, we get a plus 12x, and on the inside, a minus 12x. And then last, right, we're going to get this negative 4 times 4 is a negative 16. Well, because plus 12x and minus 12x disappear, we just end up with 9x squared minus 16. A couple of perfect squares, and sort of that fancy thing happens where the middle disappears. We get a perfect 0. Well, if we had the same idea, only this time both of them were addition, right? But the same idea that, hey, we've got an x and an x and a 2 and a 2. If I FOIL that, again, I'm going to get x squared. On the outside, it's a 2x. Inside, it's a 2x. And lastly, it's a 4, right? A 2 times 2. This time, the middle two terms are exactly alike, however. So basically, they just double, right, on there. And you might have remembered the special pattern that we have. If you do have a perfect square like that, right, technically you can say the first part squared, and the second part squared, and the first times the second times 2 always gives you the middle. So we get 2 times x times 2. Well, over here, you'll notice, well, if we've got a 16 and a 9, and we're thinking about these sort of perfect squares that keep popping up, right, in our formula, well, if I had to just take a leap and a prayer on this one, if I had to just sort of guess at it, I might think, well, 16 makes me think 4x, and 9 makes me think maybe this one's a 3. Because we have a middle term, I'm thinking it's more like this bottom pattern than it is the top one. So I'm thinking maybe this perfect square idea, right? 4x squared would be 16x squared. 3x squared would have been 9. And if I think about that pattern that we just developed in the middle here, 2 times the first times the second, right? 2 times both terms. Well, 2 times 4 is 8, times 3 is 24. And we would get exactly that 24x. Now notice it needs to be a negative 24, but we can quickly solve that by making a minus on that 3. And I believe this would work perfectly. And again, we call that, right? We call that the perfect square trinomial pattern, or perfect squares. If you have a perfect square in the front and in the back, rather than working really hard to factor this thing, what we're going to do is sort of take a leap and a prayer and say, well, x squared makes me think x, 25 makes me think 5. And if the first one times the second one times 2 will give you the middle, well, that would be 10x. Then I know that this is my pattern. Okay? Again, you get an a squared in the front, a b squared at the end. But again, 2 times a times b forms the middle. Now, you'll notice on the right here, 18 and 50 aren't perfect squares, but as sort of our checklist of factoring, I would want to start with common monomials first, right? So 18, 60, and 50, well, why don't we take out a 2? This becomes 9x squared minus 30x plus 25. And now 9 makes me think 3. 25 leads me to believe there will be a 5 here. And again, a minus 30 in the middle means I would need a subtraction. But isn't 3 times 5 being 15 times 2, right, going to give me that 30 in the middle? And then we've got that extra 2 on the outside, so don't forget to carry that down. But I think our perfect square is now factored. Again, if you have a perfect square in the front, perfect square in the back, you can take a guess, right? You can sort of hope that it works. Now, if it doesn't work out for the middle term, though, that means that we've got to kind of regroup and go back and factor it a different way. It has to work out for all three terms. Now, we already talked about this one just a little bit at the beginning. Notice I do have perfect squares, 4 and 25, only this time I don't have a middle term. And the only reason things are going to add to 0 is if, again, you've got the same terms, right? I'm thinking 2 times 2 is going to give me 4. 2x times 2x would be 4x squared. And again, 5 times 5 would be 25. But I've got to make sure that they add to 0 in the middle. I also need negative 25, which makes me think, let's make one of them positive, one of them negative. Again, that would be a 4x squared if we FOILed, plus 10x minus 25. Middle disappears, and we keep the 4x squared minus 25. So we've factored right here. Well, in that case, what we have is a nice pattern. M squared means I need m's. 9 means I need 3's. But again, in order to get a negative 9 and to add to 0, we need 1 plus, 1 minus. We call this one the difference of squares pattern. Right? The difference of squares pattern, or some books will call this the difference of two perfect squares pattern. If we have two perfect squares here, a squared and b squared, we can split the pattern into a plus b and a minus b. So again, we've got 49 and 81. They make me think 7. Right? 7x times 7x is 49x squared. 81 would be a couple of 9's. But 1 plus, 1 minus means no middle term, right? 0x in the middle. And we get a negative 81 to finish. Now, where can we take advantage of these? Well, what if we used factoring to solve? Notice over here at the left, we've got x squared minus 16x plus 64, right here. And that makes me think x squared and 64. Well, maybe this is a perfect square pattern. Don't worry about the equal to 0, although I like it equal to 0, because again, it's only worth trying to factor, right, if we're equal to 0. So that will become x, and I'm hoping this becomes an 8. And again, since it's minus 16 in the middle, again, if we check it, x times negative 8 times 2 would give us negative 16x in the middle. I know my pattern is going to work. First part squared, second part squared, first times the second times 2 gives you the middle. Which means now I can solve this. Remember, that just means it's x minus 8 times x minus 8. And if we have two things multiplied equal to 0, then either x minus 8 equals 0 or x minus 8 equals 0. Well, the answer to those, if I add 8 on both sides, is just going to be x equals 8. And really the same answer from that one, right? Just turns out I'm only going to get one solution to this because we had the same factor twice. Over here at the right, we're not equal to 0 yet. So what I'm going to go ahead and first do is subtract 3x. Then I'm going to subtract 10 as well. We're going to have 81x squared. The x terms are gone, so minus 25. Well, hey, I see an 81 and a 25. That makes me think perfect squares. And on the right, I'll have 0, which means now I think that's going to be a 9. And I think I'll also need a 5. That should factor perfectly. No middle term, which again means it's that difference of squares pattern. I'm going to use 9's and 5's to make that happen. So either 9x minus 5 equals 0 or 9x plus 5 equals 0. If I add 5 on each side of the first equation and divide by 9, I'll get 5/9. If I subtract 5, notice it's plus 5, right? So I got to subtract 5 on both sides. And then again, divide by 9. So it just so happens we get positive and negative 5/9. Again, I hope that helps you using some special patterns. Remember that when you're thinking about factoring, common monomials are the first thing to think about, such as what we did on this last screen back here. Taking out that common monomial is always a good idea. But after that, the second best thing is to think about these special patterns. Sometimes they're really easy to factor, even with that leading coefficient, right? When we have a 9x squared, or over here we had a 49. Sometimes those leading coefficients, right, like 81, make factoring harder. but special patterns can be a great shortcut. If you have any questions about factoring special patterns, make sure you talk to your teacher. Otherwise, have a great day.